Question number 2 from our velocity time graph worksheet. We want to find in question number 2 4 different things: the velocity at 6 seconds, which is a fairly straightforward one, the change in velocity, the acceleration of the object. They start getting progressively more difficult, right? They start off with an easy question, then a kind of an easy question, then a little bit tougher question, and then the last question, D, the displacement, is the hardest of the group here. These are pretty typical questions that we would get with velocity time graphs. How do we find the velocity at 6 seconds? At a specific moment in time, Kessler? We're going to go up and over, right? So if I go up and I'll go over, looks like I'm going to get about 4 meters per second. You want to find the position on a position time graph, up and over. You want to find the power on a power time graph, even though we haven't seen a power time graph, you know you'd go up and over. If you want to find the blank on a blank versus t graph, then you would go up and over. If you want to find something that's on the y-axis, all you're going to do is go up and over. If you want to find the change in something on the y-axis, you're going to do what? Up and over times 2, and then you're going to subtract the 2. So in other words, you're going to find the final velocity, the initial velocity, and then you're going to subtract the 2 of them. So what are we going to do here? For 8 seconds, the final velocity looks to be 0. The initial velocity is 16. So we're going to say 0 minus 16 is negative 16 meters per second. It's important that we have that negative on there, right? Not just 16. The acceleration of the object during this interval. Well, there's 2 ways that we can think of acceleration, although they both boil down to the same thing, right? Okay, what's one way that I can think of it when I'm finding the acceleration? What's the way that we usually say first, yeah? Sorry? Be careful with that. It's not velocity over time. I think you're probably thinking the right thing, but you're not saying it right. Yeah, it's change in velocity over time. So we could say delta V over delta T. Julie, do you remember the other way that we think of it? Yeah, the slope of the graph. But of course, the slope of the graph is delta Y over delta X, rise over run, which is exactly the same thing as saying delta V over delta T. I usually like to do it this way myself, but whatever way works for you, that's the way that you should do it. The reason I like to do it this way is because I've already found the change in velocity. It's negative 16 divided by the time of 8, which gives me negative 2.0 meters per second squared. And finally, the displacement. If you remember how to find displacement, this is actually a pretty straightforward one, right? The trick here is remembering how to find the displacement on a velocity time graph. You guys remember how to do that? Mallory, remember how to find the displacement here? Yeah, good. Find the area. And the area, because this is just a one recognizable shape, a triangle, tends to be fairly straightforward here. What's the equation for finding the area of a triangle? Danny? Yeah, 1/2 base times height, or base times height divided by 2. Good. 1/2 of the base is 8. 8 seconds times the height is 16 meters per second. Just a word of caution here. Most times our axes are measured in meters per second in seconds. But if you happen to get a graph that's measured in meters per second in, say, milliseconds, you'd have to be really, really careful to do the unit conversion there for your base, right? Because when you're doing your calculation, you want it to be in seconds. That would be rare in one of these graphs, but never know. 1/2 of 8 times 16 is 64, I think it was, right? And the units are meters. How does that work out? Meters. Isn't area meters squared? Or kilometers squared or something like that? Yep. Yeah, when we're multiplying seconds by meters per second, the seconds end up canceling, left with meters. It's not an area in the sense of, you know, in the traditional sense of area. We're calculating the area of a graph, not an actual area of space. Right? So there's no problem with it being meters as opposed to meters squared. Good. All right, the other one that we had was question number 4, I think. Now we want to find the acceleration between 0 and 25 seconds and the acceleration between 25 and 45 seconds here. Acceleration, you remember, is slope, or it's delta V over delta T. I'm going to go with the delta V over delta T again. Delta V here is 80 minus 0 over the time of 25 seconds. Technically 25 minus 0. 80 divided by 25 would be 3.2. And that's positive, right? You get a positive value there, which we should expect because it's a positive acceleration. It's a line that's sloping upwards. And finally, the acceleration between 25 and 45, same method here, either the slope or delta V over delta T. The change in velocity between 25 and 45, careful here, 0 minus 80, right? 0 minus 80 as opposed to 80 minus 0, final minus initial. Over my time interval, this time it's 45 minus 25. So I get negative 80 divided by 20, which is negative 4. If you were looking at this graph, not calculating anything, but just looking at this graph, how would you know the magnitude of this acceleration is bigger than this one? Negative, right? But how would you know that the number is bigger just by looking at it? The line's a little bit steeper, right? Although it's kind of hard to tell that by looking at the graph, the line's a little bit steeper. But the big thing that I spotted right away is the fact that, look, the change in velocity is the same, but look, the second interval is doing it over 20 seconds, whereas the first one's doing it over 25 seconds. So if you're going to cover the same change in velocity over a shorter period of time, we know it's going to be a bigger acceleration, whatever the value is. All right? How many people feel pretty good about that? You guys feel as good about that as you did the position time graphs? Because you guys aced that quiz. You guys going to ace this quiz tomorrow? Yes? All right. Again, I said the other day, the trick is, first of all, really knowing your stuff, and I think you guys do for position time graphs and velocity time graphs. But the trick is come unit test time, know your stuff, but also keep them straight. Okay, we'll have a couple practice questions prior to that unit test with things kind of scrambled around, topics kind of scrambled around just to see if you can kind of distinguish between position time graphs and velocity time graphs. Okay, quiz tomorrow on velocity time graphs. It'll be remarkably similar to the quiz that you had on position time graphs, a one-pager with a few questions just as we had on our worksheet here. All right, one quick little question here, guys. You can choose to write this down or not. This is just a little example that I want to do in class. It's nothing new. The only difference, I guess, is that it's got a few stages here. Okay, not a big deal. Again, you make the judgment. I want you to focus up here, but you make the judgment whether you copy this down or not here. I want to find the velocity at 1 second. How would you do it? Up and over. Velocity at 1 second looks to be 2 meters per second, right? The position at 14 seconds, which is a typo, it should say the velocity at 14 seconds. The velocity at 14 seconds is, we're over here to 14 seconds, 12, 14, 16, 14 seconds up and over, looks like 4 meters per second. Hey, nothing new here, right? The change in velocity between 4 and 8. Hey, what's the change in velocity between 4 and 8? Quick, simple answer. Lightning fast mental calculation here, 0 meters per second. Who said that? Hey, how do you know it's 0? Yeah, without even doing any number crunching, we know that the line is straight across, so it's at not at rest, but moving at a constant velocity during that phase. The change in velocity between 0 and 2 seconds. This is 2 seconds. Between 0 and 2 seconds looks to be 8 minus 0, final minus initial. 10 and 12 seconds. Here we're going from, looks like at 10 seconds, we're at 8 meters per second, 12, we're at 4. So we're going to say final minus initial. The acceleration between 4 and 8. Oh, quick answer to this one too. Mary, what's the acceleration between 4 and 8 seconds? 0, good. It's a flat line, right? Which means it's traveling at a constant velocity, which means it's not accelerating. The acceleration between 0 and 2. Oh my goodness, they keep going on and on and on and on. Acceleration between 0 and 2. Oh, he said the change in velocity between 0 and 2 was 8 meters per second. The time was 2, so it's going to be 4 meters per second squared. Between 10 and 12, Oh, same deal. Delta V over delta T. Oh, it's going to get uglier in a second here. Between 10 and 12, it was -4 for my change in velocity. 2 seconds, -2 meters per second squared. What's the displacement between 0 and 16 seconds? Ooh, this is the one we've been waiting for. Anybody know the equation that describes the area of this shape, this whole thing? That's how excited I was to see this question, right? It's like through my marker. What do you call that shape? I have no idea what you would call that shape. I don't even think it has a name for it. So what do you got to do? What do you got to do if you want to find the area of that crazy shape that doesn't even have a name for it? Yeah. Yeah, you got to break it down, and there's a few shapes you got to break this down into. A couple options here, but I think the most obvious one is a triangle here. Then we got a rectangle here. I got a rectangle right here, but this still isn't a shape. I think we're going to break that down like this: triangle, rectangle. Actually, we could avoid that one, couldn't we? You just call this one whole rectangle right there. Doesn't really matter. If I had it broken into 2 sections, that would have been fine as well. Area number 1 is 1/2 base times height. 1/2 of 2 times the height of 8, which is 8 meters. Area 2 is base times height because it's a rectangle. We're going from 2 to 10. So my base is 8 and my height is 8. Area 3, 1/2 base times height because it's a triangle. Base goes from 10 to 12, so it's going to be 2 for the base. And the height is going to be, ooh, what's the height of that triangle? Triangle number 3 there. What is it? Yeah, be careful there. It's not 8, it's 4 because it goes from 4 to 8, right? So that's going to be, give me a displacement of 4 meters during that stage. And area 4, we're going from, it's base times height again because it's a rectangle. The base is going to be from 10 to 16. The height is from 0 to 4. We add those up. 72, 76, 100, isn't it? 100 even. Good. If you can find the area of this one, if you can do this question we're working on right now, you shouldn't have any issue whatsoever with tomorrow's quiz. All right. First question. Did you say something? Yeah. Yeah, it would actually. Yeah, at 1 second. Yeah, you're right. That's wrong. The velocity at 1 second would be 4 meters per second. You guys see that? Okay, if you see me making a mistake like that, correct me on it on. Okay, call me on it. Because you want to make sure that either I'm right or you're right. Listen, even if you think I'm wrong and I'm not wrong, like you want to clarify that in your own mind, right? So it is 4 meters per second. Thank you. Last question. The average velocity between 0 and 16 seconds. Average velocity. How do you find the average velocity on a velocity time graph? How do you find the average velocity? Anywhere, anytime. Yeah, change in position over change in time. We just found the change in position or the displacement. And the change in time is 16 seconds. So 100 divided by 16. Let's see here. You get 6.25 or 6.3 meters per second. Good. All right, one more little thing here. We're not going to do any numbers with these at all. This is just a shape thing, and then we're going to move on to something else entirely from these graphs. This won't be on your quiz tomorrow, by the way, although if it was, you could probably be fine on it. But no, we won't throw that on the quiz tomorrow. Just some shapes of the final graph that we're going to do for a little while now. This is called an acceleration time graph. So it's acceleration at a certain time as opposed to what the velocity is or what the position is as a function of time. Notice the graphs have acceleration on the y-axis, time on the x-axis. The title is acceleration time or acceleration versus time. I marked some Physics 30 labs last night. They had it in on Friday, their first lab of the year. And out of a class of, I think there's 26 people in the class, out of a class of 26, I bet 10 of them, when they plotted their graph, titled it wrong. Okay, their graph that they plotted was final velocity. You guys don't need to write this down. Was final velocity and an initial velocity. I bet 10 out of 26, I didn't count, but I bet it was at least 10 out of 26 titled this wrong. Okay, what would the title of this graph be? You don't know how to deal with that graph, right? Final velocity versus initial velocity, but you know what the title is. What's the title of that graph? Final velocity versus initial velocity, right? Or final velocity dash initial velocity. Listen, if you knew the answer to that question, then you would have done better on that portion of the lab than almost half of the class in Physics 30 that had it in on Friday. Okay? Always y-axis versus x-axis. Which variable on this graph that you've never seen before and you won't see until next year, which one would be the manipulated variable? Most of them actually nailed that. Most of them got that correct. It was just this that people had the issue with. What would be the manipulated variable in this graph? Shay, what is it? Good. The initial velocity, how do you know that? Good. It's on the x-axis. And if we had a table of this, which one would be in the first column, final velocity or initial velocity? Initial velocity, always the manipulated variable, x-axis in the first column. All right, let's go to the shapes of the acceleration time graphs, which is really what we want to do today anyways. Acceleration versus time, it's a constant slope here. What's happening in this? If this was a position time graph, it would be constant velocity. If it was a velocity time graph, it would be constant acceleration. This is, what would you call this? Is it accelerating? Yes, it's speeding up. Is it accelerating at a constant rate? Jonah? Constant, yeah, it's kind of hard to think of what you'd say about, right? But I know exactly what you're saying. I'm not sure that I'd use that term, but I think you're thinking the right thing. Jonah said a constant acceleration of an acceleration. Let's just say an increasing acceleration. The acceleration is increasing at a constant rate. So this is like, the analogy is your foot's on the gas pedal just a little bit at the stop sign. You accelerate, right? But then you put your foot further and further and further and further down the gas pedal, and then so that eventually the gas pedal's on the floor. Not only are you accelerating over that whole time, but the rate at which you're accelerating is getting bigger. You're accelerating quicker and quicker and quicker. It's like this graph on a velocity time graph, right? Right? You're not only are you accelerating, but you're accelerating quicker and quicker and quicker. What about this one? What is it? No acceleration? No. No, that one's not right. No? No, not a constant velocity either. Okay, no acceleration, constant velocity, both mean the same thing. If we had a velocity time graph, that would mean no acceleration or constant velocity. Okay, but it's not a velocity time graph, it's a acceleration time graph. Danny? Yeah, this is a constant acceleration. So the analogy here is put your foot on the gas pedal halfway down, leave it there. You accelerate, but you accelerate at a constant rate. You're not putting your foot further down on the gas pedal or letting off the gas pedal at all. Well, this one trips people up, this last one. It doesn't have to, but it does. If you try to remember it, it's almost sure thing trip you up. If you try to understand it, you're a lot more likely to get this one right. Anybody want to take a stab at this one? Holly? Decreasing acceleration, yeah. What do you think a lot of people will say to this, about this one? Incorrectly. What do you think the common wrong answer for this one is? Yeah. It could be a negative acceleration. That would be wrong. It's not a negative acceleration at all, right? Look at this. If you go up and over here, that's a positive acceleration. This is a positive acceleration. The rate at which it's accelerating is decreasing, but it's a positive acceleration for the whole time, yeah? Some people will say a negative acceleration, but more people will say, and it means the same thing, but more people will say that it's slowing down. Okay, we see that value going down like this. People think, oh, it's slowing down. No, it's not slowing down. It's speeding up the whole time. The acceleration is above zero the whole time, but it's just not speeding up as quickly. It would be like a velocity time graph that looks like this, right? The velocity is increasing, 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 but the acceleration is decreasing. It's like you get your foot on the floor, and you're putting your foot on the gas pedal, put it all the way to the floor, you accelerate like crazy right off the stoplight, but then you kind of ease off. You still speed up, but you're not speeding up as quickly as you were before. Good.